Dear students, I welcome you for the today's lecture related to the laws of radiation in the subject of heat transfer. Basically, the laws of black body radiation, there are different laws for black body radiation. Radiation from non-black surfaces, then Kirchhoff's law, and radiation from real surfaces. The four categories one can do into the laws of radiations. But basically, when you talk laws of radiation, the laws of black body radiation, they are of more concern. And the Kirchhoff's law also, that is, people used to focus that. There are laws for black body radiation. The black body, that is a perfect absorber and also a perfect emitter. It can absorb as well as it can emit. So its total intensity and total emissive power are only functions of the temperature. That means it emits energy according to the Lambert's cosine law. When you divide these laws of black body radiation, that is the Planck's distribution law, Wien's formula, then Rayleigh-Jean's formula, Wien's displacement law, and the Stefan Boltzmann law. These are the different laws that is available for a black body radiation. If the black body is not there, that is the radiation laws for non-black surfaces, then for Kirchhoff's law, and for radiation from the real surfaces. Now, to understand this law, first one has to understand the radiation, emissivity, and the basic terminologies that is needed. Now, the nature of the radiation, what is there? We are having the this radiations, that is the electromagnetic waves, they are generated and which travel at a speed of light in terms of the photons. Energy is in terms of the photons. So these are the light is a special case of electromagnetic radiation in the small region of spectrum. The visible light as well as the infrared region is also there in this light spectrum, electromagnetic radiation spectrum. Now when the light propagates, it travels at a speed of 3 into 10 to the power 8 meters per second in the vacuum. That is a difference in the speed of light if it is traveling in a vacuum and if it is traveling into the medium. So in vacuum, the propagation of speed is CO, which is 2.998 into 10 to the power 8 meters per second. A huge speed. Then if the medium of propagation, the speed is C, and this C is less than C0, because in a vacuum the light propagates at a faster speed as compared in presence of a certain medium or a certain atmosphere. And this difference in the speed of propagation of light in the vacuum to the speed of propagation of light in the medium, that is termed as the refractive index N. So N, which is equal to C0 upon C. And for gases, N is approximately equals to the 1, and for glass, the N is about 1.5 times. So C0, that is the speed of light in vacuum, that is nothing but equals to the lambda wavelength into the mu frequency. We have already studied this lambda into mu. Then according to the quantum theory, the thermal radiations propagate in the form of discrete quantas. That is the photon, and the energy associated with these quantas, that is E, which is equal to the h into the mu. H mu, that is the energy associated with this radiations, quantum of radiations, where h is the Planck's constant, mu is the frequency of quantum. Then each quantum of photon may be considered as a particle having the energy, mass and momentum just like the molecules of a gas. And that is why we are using E, which is equal to h mu. The radiations can be considered as a photon gas flowing from one location to the another with its particles governed by the relation E, which is equal to mco square, that is equal to the h into the mu. So mco square, which is m, which is equal to the h mu upon co square, and also the momentum, which is nothing but the mass into the velocity. So mass, which is h mu upon co square, h mu upon co square into the c0, velocity of the light. So it has, this will not be there. Then Boltzmann showed that the flux of heat energy emitted by radiation from an ideal surface called the black is proportional to its absolute temperature to the fourth power. This is the Stefan Boltzmann constant, that is there, sigma, and it is having the value of 5.669 into 10 to the power minus 8 watt per meter square Kelvin, where QB, that is the quantity of energy emitted per unit area and per unit time, that is energy emitted per unit area per unit time. Energy emitted, energy is having the units of joules. When you talk joules in upon the time, that becomes your watt. So Boltzmann showed that the flux of heat energy emitted by radiation from any ideal surface called the black ideal surface, that is black surface, that is why we call it the QB for the black surface, the quantity of energy emitted by a black body, is proportional to its absolute temperature to the fourth power, is proportional to the absolute temperature of its fourth power, where temperature is in the absolute Kelvin. Then the emissive power and the monochromatic emissive power, EB lambda. Emissive power, that is the EB, and the monochromatic emissive power, that is the EB lambda. EB is our emissive power for a black body. Emissive power for a black surface is the EB, is the energy emitted by the surface per unit time per unit area. That is what is the emissive power, joules per second per meter square. So emissive power of a black body depends on the surface material and its roughness. So this emissive power EB, which is equal to the QB, that is the amount of quantity of energy emitted per unit area per unit time. Amount of quantity emitted, which is equal to the emissive power. It is necessary to determine the spectral distribution of energy radiated by the surface. At any given temperature, the amount of radiation emitted per unit wavelength varies at a different wavelength. So it's a function of a wavelength. So monochromatic emissive power EB lambda that is the rate of energy emitted per unit area of the surface per unit wavelength, watt per meter square into the mu. So this mu term that is also coming because of this monochromatic emissive power. Lambda is indicated by a monochromatic emissive power for a black body. EB is our emissive power, and EB lambda is the monochromatic emissive power for a black body, and which is nothing but the rate of energy emitted per unit area of the surface per unit wavelength. So this EB, which is and having the unit of watt per meter square mu, and EB is having the unit of watt per meter square. So you can multiply it by the lambda difference, and this is for the integral from 0 to infinity for the complete range. The next is the intensity of radiation. There are two types of intensity of radiations. The black body emitting radiations in all directions can be visualized by considering an elementary area, a certain area that we are considering, and the radiations will be wholly intercepted by the hemisphere of the radius. So these two types of intensities, the spectral radiation intensity and the total radiation intensity. The two types. The spectral radiation intensity is defined by IB lambda, and total radiation intensity is defined by the IB. So the spectral radiation intensity IB lambda is defined as the amount of energy streaming through a unit area projected normal to a given direction per unit time per unit solid angle about the direction and per unit wavelength about the wavelength lambda. And the total radiation intensity IB, that is used to characterize the amount of energy emitted over the entire wavelength of the spectrum. That is, for the entire wavelength from 0 to infinity, lambda is from 0 to infinity, entire wavelength, and that is why we are integrating this spectral radiation intensity and multiplying it by the d lambda, where d lambda is the radiation in a small interval. So this is the two intensities, that is the spectral radiation intensity and the total radiation intensity. Then let us understand the Lambert's cosine law. A diffuse surface radiates energy in such a manner that the rate of energy radiated in any particular direction is proportional to the cosine of angle between the direction under consideration and normal to that of the surface. So EB, which is equal to the emissive power of a black body, which is equal to pi into IB. IB is nothing but the radiation intensity, total radiation intensity, which is nothing but the sigma into T raised to the 4. Similarly, if you talk in terms of a monochromatic emissive power for a black body, that is which is equal to the pi into IB lambda, which is nothing but IB lambda is nothing but a spectral radiation intensity. That is all mentioned here. Then coming to the first law of the black body radiation, laws of black body radiation. The first law is that of the Planck's distribution law. Now this Planck's distribution law, it is the spatial distribution of radiation intensity of a black body is given by this EB lambda, which is equal to the pi into IB lambda. So this spectral distribution of radiation intensity of a black body is given by it can be written as which is equal to 2 pi c1 upon lambda raised to 5 into e raised to c2 upon lambda t. where C1 and C2, that is, they are the constants, and HCO square, which is equal to the 0.595 into 10 to the power minus 8 watt per meter square, while C2, which is equal to H into CO upon K. K is the Boltzmann constant, and having the unit of 1.438 into 10 to the power minus 2 meter Kelvin. And if the magnitude of the emitted energy at each of a wavelength which comprises the whole radiation. This is the graph, that is relative power is given as a function of a wavelength for different temperatures. This is for the different temperatures. Now this is the visible region that is observed. The energy emitted at all wavelengths increases with the rise in temperature. This energy emitted, relative power, that is the energy emitted, EB lambda is the energy emitted, nothing but the emissive power, EB lambda, that is the energy released, energy emitted, that increases with the increase in the temperature. And the peak spectral emission power shift towards a smaller wavelength at a higher temperature. As we are increasing the temperature, the peak of all these graphs, that is, this is your peak, all these peaks, they're moving towards the left side. This is moving towards this left side, and peak spectral emissive power shift towards a smaller wavelength. Left side means that is a smaller wavelength as we are increasing the temperature. Then when the temperature of a body is varies, not only does the quantity of emission changes, but also its distribution over a wavelength band. That means initially for this 20 degrees Celsius, there is nothing is observed in this visible region at 20 degrees Celsius. But as I am going to increase the temperature to the 600 degrees Celsius, some radiations that can be observed in a visible region. This is our infrared region, and this is the visible region. So as we are increasing the temperature, we can observe or go into the visible region. If for a body at 600 degrees Celsius, only small quantity of energy is in the visible region, when its temperature is further rises, its color also changes. Same body is there, but because of the temperature, we can see the different colors. This is also studied for the gold. It is prominently observed at room temperature, say around 30 degrees Celsius, the gold is a golden metal. But at different temperatures, it can be green or red. It goes into the different visible region. That is a function of a temperature. Even on the size, if you go towards the nanoparticle size, the color of the gold that also changes. Then this is the monochromatic emissive power, EB lambda, upon T raised to 5, which is equal to the pi into IB lambda. IB lambda, that is nothing but the spectral radiation of intensity, which is equal to the same equation 2 pi C1 upon pi T raised to the 5 e raised to C2 upon lambda T minus 1. This is the same equation. You have to remember this equation of to solve the different numerical problems or to discuss the different derivations associated with the radiation unit. So this equation, basic equation, is the only modification. At different situation, depending on the situation, this basic equation that is going to be varied. Here it is divided by t raised to the 5. So we have here also t raised to the 5 divided by, no change, the equation is same one. Then there is a Wien's formula. This is applicable for the small wavelengths. Small wavelengths, that means the lambda is very less than the 1. Small wavelength, that is lambda, that is very less than the 1. So the denominator value e raised to c2 upon lambda t, that will be very greater than 1. As I am going to substitute this smaller value of the lambda, so this value, total value, that will be very greater than the 1. So greater than the 1, and you have to subtract the minus 1 from this basic formula. C2 upon lambda t minus 1, that will be there. So this is going to reduce to the IB lambda upon t raised to 5, which is equal to 2 times C1 upon lambda t into e raised to C2 upon lambda t. This is the same thing. I have provided the formulae which will not confuse you. This thing is same as this thing. Then third is the third law for the black body. This is when the lambda is very greater than 1. For small wavelengths, lambda very greater than the 1. That is, lambda is the large. This is not small, this will be the large. So C2 upon lambda t will be very less than the 1. And the expression e raised to C2 upon lambda t, that has to be expanded in a Taylor series expansion. This is e raised to C2 upon lambda t minus 1, which is equal to the 1 plus C2 upon lambda t plus 1 upon factorial 2 into bracket C2 upon lambda t raised to 2 plus factorial 3, 1 upon factorial 3 plus C2 upon lambda 2 raised to 3 plus dash. Now here all these higher terms of C2 that can be neglected, and the remaining will be the C2 upon lambda t. So this e raised to C2 upon lambda t minus 1 will be equals to the C2 upon lambda t. So the equation, above equation, that reduces this equation, that reduces the C2 upon 1 in the denominator. So this is C1 upon C2 into lambda t raised to the 5. And IB lambda upon t raised to 5, which is equal to 2 times C1 upon C2 into 1 upon lambda t raised to the 4. Then the fourth law is the Wien's displacement law. That is, for the black body emissive spectrum, the wavelength lambda maximum giving the maximum power at a particular temperature is obtained by differentiating the equation with respect to the lambda and setting it to the 0. For optimization purpose and for getting the maximum value, generally we differentiate the equation with respect to the particular and equate it to the 0. So lambda max t, which is equal to the C2 upon 5 into 1 minus e raised to minus C2 lambda max into the t. So by simplification you will get the lambda max t, which is equal to C3, which is nothing but 0.289 into 10 to the power minus 2 meter Kelvin. So similarly the EB lambda max upon t raised to 5, that will become equals to constant, and so EB lambda max, which is equal to C4 raised into t raised to 5, where C4 that is the constant and having this value. The next is Stephen Boltzmann law, the fifth one, that is related to the total radiation intensity. It follows from the definition of the total radiation intensity, that is nothing but IB, which is equal to the from lambda from 0 to infinity IB lambda into the d lambda. That is the total radiation intensity is the IB, lambda is your wavelength, and IB lambda is the spectral radiation intensity. So integrating this IB lambda, that is to be substituted from the above equation, that is obtained from the Planck's law equation. You have substituted it, and then after integration of substitution, it simplifies, and you will get the total emissive power or a hemispherical emissive power of a surface, that is EB, which is equal to from 0 to infinity EB lambda into d lambda, which is nothing but 0 to infinity pi IB lambda into the d lambda, which is sigma t raised to 4. So this is the Stephen Boltzmann law. Then there are different laws related to the non-black surfaces. When the radiations from non-black surfaces are there, then the emissivity term is of more concern. Emissivity of a surface is a measure of how it emits radiant energy in comparison with a black surface. It is basically related to the emissive power only, but it is the ratio of the emissive power of actual surface to the emissive power of a black surface at a same temperature. That is, the emissivity of a surface is a measure of how it emits radiant energy in comparison with a black surface at a same temperature. That is related to the energy, emissive energy radiated. So in reality, the emissivity of a material varies with temperature and the wavelength of a radiation. So it's a function of temperature and is a function of a wavelength. So when it's a function of a wavelength, that becomes, we are calling it a monochromatic emissivity. That is the sigma lambda. That is the ratio of monochromatic emissive power. Now E lambda is your monochromatic emissive power of the surface to the monochromatic emissive power of a black surface at a same temperature and at a same wavelength. Then there is a next term that is related to normal total emissivity epsilon n. So this epsilon n, that is the normal total emissivity, it is the ratio of the normal component of the total emissive power of a surface En to the normal component of total emissive power of a black body Ebn at a same temperature. And so epsilon n, that is the normal total emissivity, which is equal to the normal component of the emissive power to the normal component of the total emissive power of a black body, that is Ebn. Then there is a gray body. When monochromatic emissivity of the body is independent of a wavelength. So it's not a function of a wavelength. That is, only the E will be there. So emissive power of a body is related to the monochromatic emissivity epsilon lambda by the given concept formula. So this emissive power, emissivity of a surface is a function of its nature and characteristics and is independent of a wavelength or the nature of impinging radiation waves. The next is the Kirchhoff's law, that is giving a relationship between the emissive power of a surface to its absorptivity. It is a relation between the emissive power and the absorptivity. Alpha, that is the absorptivity, E is the emissive power. So E upon alpha, that is the emissive power upon the absorptivity, that is equals to the G, that is the rate at which the energy falls from the walls on the body. That is the relation between the emissive power of a surface to its absorptivity. Emissive power to the absorptivity, E upon alpha, this Kirchhoff's law. Suppose that a small body is placed inside a large evacuated enclosure, the walls of which are maintained at a certain temperature T. Heat will be exchanged between the body and the enclosure until the equilibrium is established. So there must be a certain equilibrium that will be established between the body and the enclosure. That is, when both the body and the walls of enclosure have reached the same temperature, then the body will emit as much energy as it absorbs. That is what? The amount of energy emitted will be same as the amount of energy absorbed. That means we can say the two bodies are in thermal equilibrium, or they have established the equilibrium. Then the body will emit as much energy E as it absorbs alpha. And this Kirchhoff's law at equilibrium ratio of the total emissive power to the absorptivity is the same for all bodies. That is, if alpha is less than the 1, emissivity and absorptivity is a function of a temperature. So at a given temperature, the emissive power will be the greatest for a body when alpha will be equals to the 1. And at that situation, E that will be equal to the EB. Emissive power will be equals to the emissive power for a black body. Then the total emissivity, which is equals to the E emissive power upon emissive power for a black body. So E upon alpha, that is equal to the EB upon 1, which is equal to the E upon epsilon. So at thermal equilibrium, the absorptivity and emissivity of a body are equal. That is, the absorptivity alpha B of a black body and the emissivity of a black body, that will be equals to the 1. That means they are in equilibrium. At equilibrium, this Kirchhoff's law talks of equilibrium. So Kirchhoff's law in terms of monochromatic thermal radiations at a given temperature T and wavelength lambda is given in terms of the epsilon lambda, which is equal to the alpha lambda. That means the monochromatic thermal radiation, monochromatic emissivity with the thermal radiations will be same as the absorptivity with that monochromatic radiations. So this is all about the different laws of radiation.